All right, so now that we have enough tools in our mathematical toolbox, we can actually start to explore this world of the RSA crypto system. So in this case, RSA is actually a nice little reference to the three founders of this crypto system, namely Rivas, Shamir, and Adelman. So in the case of the RSA crypto system, we're going to have this one really important player. In this case, I'm going to call this person Bob, or B for short. So it's going to be Bob's goal to actually come up with some way or some technique to actually tell the entire world how they can actually send a message to Bob. So in this case, what he wants to do is he wants to say, okay, if you want to send me a message, do a bunch of stuff and send that message to me. I'm going to do it in such a way that I'm going to be the only person that knows how to decode whatever message you just sent me. So in this case, what's going to happen is that he's going to have to make some information publicly available. So in the case of the RSA crypto system, he's going to be releasing two really key pieces of information. In this case, he's going to be giving out some number, which we're going to call an E, and he's going to be giving out another number, which we're going to call an N. Those two numbers together are going to be referred to as this public key. So in this case, Bob is letting everybody know, hey, if you want to send me a message, you're going to be using those two little pieces of information. You're going to use that stuff in such a way that you're going to encode whatever message, send it back to me, and I'm going to be the only one that knows how to decode this. So in this case, these numbers E and N are actually somewhat suggestively used notations in this case, in that E is actually going to be some exponent, so in this case E for exponent, and that little number N is actually going to be this number that we're going to be reducing things modulo. So in this case, we've been using N's over and over and over again, so it seemed natural just to use an N again. So in this case, if I'm another person, let's say I'm Alice. If I wanted to send some message to Bob, so in this case, I'm going to think about some string of numbers, whether it be a social security number, a birthday, or a phone number, or whatever kind of credit card number, whatever random string of numbers I want to send. That's just going to be my message X. So in this case, obviously, I don't want to just send X to Bob just on this open channel, because what could happen is I could actually just have some eavesdropper. In this case, I have this evil person named Eve who could intercept this message. In this case, if I don't encrypt this thing somehow, they know immediately what that number is. So in this case, that's not what I want to do. So what's going to happen is that she's going to take this little message X and she's going to encode it in such a way so that she can actually send it to Bob and Bob knows what she's trying to say. So in this case, what she's going to do is she's going to go into her giant database or Rolodex or whatever random storage information she has on all of these people that she wants to talk to. So in this case, she's going to thumb through all these accounts and find Bob, and she's going to pull out Bob's card, and she's going to say, oh, Bob is requiring me to use this exponent of E and this N as my modulus. So in this case, what's going to happen is she's going to take this little message X. She's going to raise it to the power of E, so this is the power that Bob said to use, and then she's going to reduce this number modulo N, which is the N that Bob said to use. So in this case, she's going to create some new number, which is going to look very strange to her. It's going to be this garbled message, which in this case is going to be some Y, and she's going to take that number and send it to Bob. All right, so then what's going to happen is that I'm going to now view this role of being Bob. I'm now going to receive this little random message Y, and I'm going to be, okay, now what do I do with this thing? I want to decode this thing somehow. So this is where a lot of kind of prep work is going to go into play. So what's going to happen is that Bob's going to release these numbers E and N. And they're going to be, in a sense, randomly chosen numbers, but there's going to be one very special number that comes into play in all of this. And that's going to be this secret decoder, which we're going to reference as a D. So that D is going to pair very nicely with the E and the N. They're actually all going to be chosen in a sense at the exact same time. But that D is going to be only known by Bob. And that's the really important thing, is that Bob can be the only person that knows what D is. The moment somebody else knows what D is, all bets are off. This whole system breaks down. So this is the thing that Bob really needs to keep close to his chest. He doesn't want to let anybody else know what his secret decoder is. So in this situation, what's going to happen is that Alice is going to send this message Y to Bob. Bob's going to receive this new message Y, and he's going to be like, okay, now I just need to decode this thing. So what's going to happen is he's going to take this Y, he's going to raise it to the power of D, and then he again is going to be reducing this modulo N. And if everything was done correctly, this hopefully should kick out that original message X. So this is where you can kind of see this whole little process come into play. What's going to happen is that Alice is going to have her message X, which is some random string of numbers. She's going to raise this to whatever exponent Bob said. She's then going to reduce this modulo N, which is the N that Bob said to use, and she's going to get this new random message Y. And she's going to think that that looks really weird. And what's going to happen is she's going to send that horrible mess off to Bob. Bob's going to say, okay, thank you. I'm now going to secretly do this off to the side so nobody sees what I do. I'm going to take that number, raise it to the dth power, and reduce it modulo N. And hopefully a message of X emerges at that stage. So you can see in this situation, this question of inverses comes full circle. The idea is that that original message X is encoded, so it's going to be going through some function, and it's going to kick out a Y. And then this decoding function is going to take that message Y and convert it back to the original thing. So in this case, a function and an inverse are all in play. So that's where we're going to be living. We're going to be thinking about how can we choose this public key and actually find this special little decoder in such a way that we're going to keep this question of inverses floating around. And in this case, everything is going to be built out of this question of what is n, or what should I choose n to be. And so again, we want to think back to this question of there's a lot of information that's actually going to be publicly available. Bob is giving out quite a bit of information. Alice is also giving out quite a bit of information in the sense that Alice is actually telling you what her garbled message is, and she's telling you how she actually garbled that thing up. So in a sense, she's given out quite a bit of information. She's hopefully really trusting Bob that his system is actually pretty secure because she's putting a lot of faith. If she's sending off her, social security number or credit card number, she's encoding this in a way that she hopes Bob's doing what he's supposed to be doing, and he's keeping this little D safe. So in this case, I did try to draw this D in this nice little safe, though I'm pretty terrible at drawing. So in this case, that's a safe handle. So D is hopefully kept really safe. So in this situation, what's going to happen is that we want to think about inverses floating around. So in this case, we want to be thinking about what types of n's should we actually choose. And in this case, the bigger the n, the better the system is going to be. But I need to know an n that actually has this potential to see some of these inverses floating around. And this is actually going to be where this Fermat's little theorem, or at least the corollary of this thing, is going to come into play. The idea that if I take this n to be a product of two really large prime numbers, I at least have some information on what are some things that actually bring about some of these inverses. I know at least where to look in that situation, or at least what powers to raise things to. So that's what that n is going to be, is it's going to be a product of two very large prime numbers, and then that e is actually going to be chosen to work very nicely with that exponent of p minus 1, q minus 1 that we actually saw in that corollary to Fermat's little theorem. Okay, so let's go ahead and see how we can actually create that little key. So in this case, what we're going to be doing is we're creating this public key as well as this private key. So in this case, this is all the information that Bob's going to do way before Alice has even entered the situation. So in this case, what's going to happen is that you're going to choose two very large prime numbers. In this case, call them p and q. And for the example that we're at least going to run through this, I'm going to choose two very small prime numbers because it's bad enough doing this computation by hand. It's even worse when you have these massive numbers to be working with. So in this case, I'm going to choose p, let's say, to be 233. And I'll take q to be something like a 151. So in this case, if you were to actually use this in practice, these would be terrible numbers to use because they factor, the product of these two things factors way too easily. So it's a terrible collection to use. But like I said, it's bad enough doing some of this by hand. It's worse when you start choosing these things to have tons and tons and tons of digits. So the first thing that we're going to do is we're actually going to compute this n, which is simply computing p times q. And that's really easy to do. And that's the full power of this crypto system, is that multiplying things together, really easy. If you actually give me two numbers that have been multiplied and say, okay, go and factor it, that's really, really hard to do. In this case, it's not so bad if it's a 5-digit number, but if it's a 50,000 digit number, that becomes way worse. So in this case, like I said, just test little numbers because they're easy to work with. They're chosen somewhat specifically so that this whole process becomes not so bad. So in this case, multiplying these by hand is going to be 233 multiplied by 151, which is going to kick out a 35,183. Okay, so that is half of the information that Bob is going to release. That is the number n that is part of his public key. So the next thing he's going to do is he's going to create this exponent that he wants people to use. So in this case, he actually has the freedom to choose whatever type of exponent he wants to use. There is one small little caveat, though, that must be followed, is that this exponent, e, should play very nicely with that exponent that we saw back in that corollary to Fermat's little theorem, namely this product of p minus 1, q minus 1. And the rule that I want these things to do is I want those things to be relatively prime. That is, I want the greatest common divisor between those things to actually be a 1. And the reason for that is that that's going to come into play when I actually come up with this secret decoder, in that I'm actually going to run this extended Euclidean algorithm to actually give me the inverse of e modulo this p minus 1, q minus 1. So in this case, I do need to know that those things are actually going to be invertible elements in this modulus case. So what I need to do is I need to think about what is this random little exponent going to be. So it's going to be p minus 1, which is 232. 232, not a 3 again, 232 because it's 1 less than that prime, multiplied by 1 less than this prime, which is a 150, which at the end of the day is going to be 34800. So this is a number that Bob does not want getting out there. This is something that's also going to be at least temporarily used as a secret number, but once he's done with it, he should shred this, because if somebody knew this number, all bets would be off. They'd have way too much information that they'd be able to break that thing pretty quickly. So in this case, I just need to choose some exponent that's going to be relatively prime to that number. So in this case, you're free to choose anything you want to. You might as well choose something that's somewhat small so that the people, when they actually have to encode these things, they don't have to take numbers raised to massive powers in a sense. So in this case, let's choose maybe a small little exponent. Let's say 17. So 17 is a prime number, and 17 obviously does not divide nicely into 34,800. So those two numbers are in fact going to be relatively prime. What I want to do, though, is I want to find what is the inverse of 17 modulo this giant product. So in this case, what I'm trying to do is I'm trying to find this special number y such that 17 times y is going to kick out a 1 modulo this product of 34,800. So in this case, that little y is going to become my d in this case. So what I want to do is I want to run this nice little Euclidean algorithm on this pair of numbers 34,800 and the number 17. So in this case, this is where you can really see that I chose some pretty specific numbers, because it's bad enough doing this by hand. It's worse when I have to do a ton of steps in my division algorithm. What's nice about this is that if you take 34,800, so 34800, and you divide it by this 17, it's going to kick out 2,047. And if you take 2,047 and multiply it by a 17, you can see that it's going to kick out a 34,799. So it's already 1 away in this case. So you very quickly find out your remainder of a 1 is going to pop out. So the full Euclidean algorithm only takes 1 step. So this is where I didn't want to do a whole bunch, because it's bad enough doing these gigantic numbers. It's worse when I have to do a whole bunch of rows of this situation. So in this case, I know that 34800 is going to be this 2047 multiplied by a 17. And here's my nice little remainder of a 1. So in that case, I can rerun this thing on this new pair of 17-1 if I really wanted to, even though you can see that I'm done at this stage. So a 17 is a 17 times a 1 plus a 0. The last non-zero remainder is going to say, hey, there's my 1. So I do have a greatest common divisor of a 1. And more importantly, what I see is that 1 is going to equal 34800. And then I'm going to subtract off a 2047 times a 17. Which, if I really wanted to, I could view this as, in this case, a 34800 times a 1 plus a 17 times a negative 2047 is going to be a 1. So in this situation, if I look at this equation modulo that 34,800, so I'm going to switch colors here, what's going to happen is that that component would go to a 0, because it obviously is that 34,800. So in this case, what's going to happen is I end up with a 17 and a negative 2047 is going to kick out a 1 modulo 34800. So in this case, that is that special little number that I'm looking for. Except for in this situation, I'd like to work with something that's actually positive, because that little d is actually going to be an exponent in this world of this secret decoder, and I don't want to be dealing with these negative exponents. So what's going to happen is that this d is going to actually be this number, but I'm going to look at its positive version of this thing. So I'm going to take this negative 2047 and add 34,800 to it. So what's going to happen in that situation is that I'm going to actually get something that's positive, and it's going to become my exponent. So in this case, my d is going to be 32753, which you can see is actually going to be congruent to that negative 2047 in this mod 34800. I'm actually free to choose any d that satisfies that thing. I'm just going to choose the first positive one. So in this case, the first positive one still ends up being a fairly large number, but oh well, like I said, it's a secret decoder that only Bob has to deal with, so he, I guess, is at fault for choosing that number. So in that case, my d is exactly that number. So 32753. And that's the thing that he wants to keep close to the chest. If anybody else knew that number, they would immediately know how to decode any message that was sent to Bob. So in this case, if I ended up being this eavesdropper, this kind of person, Eve, who has this fun little hat, she is currently missing this secret key. If she all of a sudden had that key, she could decode any message that was sent to Bob, and this whole system would break down. So Bob really does want to keep that D secret. Okay, so that is the RSA key choice. The idea is that that's all you have to do behind the scenes. And then once you have all of that, you can publish those two key pieces of information. You can publish the E and you can publish the N. And now everybody knows how to talk to you and you know how to decode those things. So in this case, all right, let's go to the official, that's my written out version of that thing. Okay, so what's going to happen in this situation again is that if Alice wants to send some message to Bob, she is going to come up with some random string of numbers. So let's say Alice wants to send the message of 24024. If she wants to send this message to Bob, what she's going to do is she's going to take 24024, raise it to the 17th power because that's the number that Bob published is 17. And then she's going to be reducing that number modulo whatever random modulus that he was working with. So in this case, it was that product of that P times Q, which in this case was 35183. If she does this reduction, which is pretty bad to do, but it's doable, at least in this case, what's going to happen is that it's going to kick out the number 9,307. So that becomes the Y that she sends. So what's going to happen is that she sends that message to Bob, and she's going to, I should put that up there, 35183. Okay, so that's the public information that Bob presented. So now Bob's going to take that number Y, I'm going to switch colors here, and he's going to try to decode this thing. So in this case, if I take 9307, and if you raise this thing to this massive power, which is probably going to take some computation, some somewhat sophisticated computational power, what's going to happen is you take 9307, and you're going to raise that to the power of 32753, and you're going to reduce that number modulo 35183. What you hope to see is if you compute that thing, it's going to kick out a 24024, which is exactly what the original message was. So in this case, there's a couple key pieces of information that you're going to want to see, is that there's obviously going to be this need or this interest in actually being able to compute some things to relatively large powers. Obviously on Bob's side, the thing he does not want to do is try to take this number and raise it to that power and then do the modulus step. What you want to do is actually try to think about what are some of the guts underlying this to make this exponentiation in this modulo world a little bit more efficient. And that's a little bit beyond the scope of this course to actually try to compute some of these things. A lot of the programming software that we work with actually can do that relatively efficiently. So if you want to, you can do this in Sage. You can actually even do it in Wolfram Alpha, that they actually have some of this pretty powerful actual kind of large exponentiation tools in there. But there are some pretty sophisticated algorithms that actually tell you how you can reduce some of these things relatively quickly. So in this case, for now, it's going to be a little bit of that kind of black box kind of magic step that's going to say, okay, plug it into that and it should kick out what it should. In this case, we're more interested in why is it actually going to work. So in this case, everything is built up in such a way that it does properly kick out what it should. So in this case, I actually do have that formal process kind of written out in my typed out notes in this case. So you can see those steps on what should Alice actually send to Bob. So she's interested in sending the message 24024. She's going to raise this thing to that power. So in this case, it's going to compute that giant mess, sends that number to Bob. Then Bob's going to try to decode that thing. So here's where that gross step of actually computing that thing to a massive power comes into play. And you can see that he does actually read off the correct message that Alice tried to send. So in this case, that number could mean anything you wanted to. So in this case, 24024 actually is the letters YAY, which is the message that she maybe was trying to send. Or it could be some random garbled mess still, 24024. If you put that into letters, it's not as meaning if you just go one by one. So in this case, let's say she was trying to send the message yay, or she was just trying to send those 5 digits. In this case, maybe it was a zip code or something like that. So this last little bit, if you're interested, it actually does have the slightly more formal version of what makes this RSA system actually work. The idea is that if you've built up all of these things like we've mentioned, I actually do want to see that these things are properly inverses of each other. So in this case, if I know that y is going to be this x to the e modulo n, what I want to do is I want to see that if I take this y like this and raise it to the dth power, so in this case I'm going to have x raised to the de, because in this case I'm raising both of those sides to this power, what I'm hoping for is that this part at some point in time is going to kick out an x again. So in this case, if you're interested in going through all those steps, I do have the slightly more formal version of this kind of all going into play. It's a little bit technical to see all those steps, but at least it's worth kind of at least having one quick glance at it so you can kind of truly believe at least the kind of the pretty sophisticated mathematics that are sitting behind this pretty popular RSA crypto system. So there's this idea of really trying to show why those things are actually inverses of each other. You do properly see this nice little product P-1, Q-1 coming into play. And then it does finish off pretty nicely that everything collects, and at the end of the day, it does actually properly show that that thing is an inverse. So in this case, it's pretty advanced to actually see all those little pieces coming into play. For now, I want you to actually see if you can actually construct these keys and see this kind of Euclidean algorithm come into play to actually identify these inverses and things like that. But the inner workings, the real true guts of that is actually something that we can attack in a course like this. And it's pretty neat to see that, something in a 200 level math class is something that is really at the guts of what makes internet security so important. And it's not that long of a proof, actually, which is somewhat frightening to think about, is that, man, there's not a lot of work that actually goes into this. And this is the whole process of, me sending off social security numbers and all this information on the web as kind of, I really hope this is actually working. And what's cool about it is that it actually does. So in all of this, like I mentioned, the big kicker in all of this is going to be that little n. The idea is that that n is going to be some product of two prime numbers. And if I knew what those prime numbers were, everything would break down. If I'm this kind of interceptor in this case of trying to kind of creep on this system and trying to get in Bob's head, if I knew what that n factored into, I would have too much information and then I'd be able to crack everything. So in this case, we do really want to think about n as being some product of two massive prime numbers. And for now, at least, we don't have super efficient factoring algorithms. So the idea of trying to factor some of those things is a little bit beyond what we can do now. But at some point in time, if a super efficient factoring algorithm comes into play, or we have quantum computers that can do some of this, we're going to have to revisit this question of how can we look at some of these crypto systems? Because inevitably, this system is going to break, or somebody's going to come up with some way to attack this thing. But for right now, it's a pretty slick little tool to see. But the idea of kind of the randomness and absurdity of some of these prime numbers is probably inevitably going to be around in whatever crypto system replaces RSA. So having kind of the inner workings on what's going on there is going to be at least nice to kind of in 5 to 10 years, whenever that next system comes into play, we at least know how to attack that thing.